Well, hello again. My name is Katina Michael. I'm the co-chair of the IEEE Society on the Social Implications of Technologies, Socio-Technical Systems Technical Committee. And today, together with Arizona State University, we will have a guest lecture by BrainChip Inc. Now, BrainChip has already spoken to us about neuromorphic computing. And today we learn about their software development kit and the way you conduct machine learning on these neuromorphic computing chips. This is on the MetaTF platform that allows you to do things like use wake words on edge devices and look at the potential implications for smart cities. This is the Computer Science and Engineering 598 and Human and Social Dimensions 598 Smart City Infrastructure and Technology. That's part of the National Science Foundation's National Research Training Award that was handed down. We've got about 30 PhD students engaged in this classroom working towards a care platform, mentored also by Dr. Robert Abbas, the chair of this technical committee. We have Todd Vieira, Nikunj Kotecha, and also Chris Anastasi, a senior product engineer, who's come to us today to talk to us about MetaTF and how you would go about using the developer notes online on brainchipinc.com/developer. If you need support or you need to learn more about Akita, you can reach out to the team at BrainChip. But in this situation, we're going through an academic program, a university program, whereby together with Carnegie Mellon University, a second affiliate of BrainChip in their academic program, ASU and ASU students are being mentored through and learning about MetaTF, the benefits of neuromorphic computing, especially with respect to energy and the ability to do simultaneous transactions towards inference and prediction. So all neural networks, all to do with machine learning, all to do with looking at sensing the environment and how that might help us develop a care platform. I hope you enjoyed the lecture, and over to our guest lecturers, Todd Vieira, Nikunj Kotecha, and also Chris Anastasi. Thank you.
Okay, so we also have Chris Anastasi in the room.
Sure.
He's our senior field applications engineer from BrainChip. So typically these workshops, Chris and I give them together. And if you guys have any questions along the way, he's also capable of answering them, and he'll be moderating the session while I'll be talking to you guys. So that way, you guys can get your answers right away. And again, at the end of the session, if you guys have any questions, we'll go over those stuff as well. What do you want to say, something?
Yeah, I just want to thank all you guys for coming again. You have, this is the next step. The first step lecture we had was an overview of the technology. And today we're really going to get into our software development kit. So you guys should all be able to start developing your networks on BrainChip Akita. So with that, I'll hand it back to Nikunj, and he can start the lecture too.
Yeah, let me just share my screen. And just to confirm, Katina, we still have until 2 p.m. today, right?
And even 15 minutes on. So I know we've kept you 10 minutes and your time is extremely precious to us. But yes, we have until 2:45 Arizona time.
And primarily what we plan to give you guys is an overview of MetaTF, list out the packages that we have in MetaTF, how do we use that, and have an example that will go along with it. It's an MNIST-based example of how do we convert, regular networks to our platform, and some other additional stuff on running it on the hardware, additional features that our board has in terms of running the inferences, that just some hardware features as well. And towards the end, we have some use cases to go over. Different modalities, vision, audio, vibration. So just want to give you an overall background over what these use cases, how we implemented some of our models which are in our model zoo for these use cases. So kind of gets many of these students a head start on how do we view such examples. And then towards the end, we can have some questions as well, if I cannot get to them during the presentation. So just to skip this one, just to kind of go over our machine learning framework, MetaTF, we essentially have three Python packages. One is the Akira one, which is on the center one. The second one is the CNN to SNN. As you can see, it works a lot with TensorFlow Keras. And the third one is the Akira models. It has a lot of model zoo that are pre-trained for Akira, and a lot of other functionalities like pruning, or if you're aware about knowledge distillation, we can use those things specifically for Akira. And I'll dive into all these in more in detail in the next slides. But essentially, when you land on MetaTF, on the left, what you see is a lot of other important resources. So in terms of how do we install these packages on the Linux systems, these are all Python-based packages. Some user guides on how do we for each of these packages, some details are mentioned, some layer restrictions might be there, some constraints might be there. So very good resource to look for. Many other examples in terms of code. So these are live Jupyter notebooks that you can actually download, run it on your own systems. You can play with them, get examples of transfer learning, of implementing one-shot learning, regression models, so on and so forth. And what I also like to do see is change log. So right now we're running, I think, MetaTF 2.2.3. So anytime a newer version comes about in any of these packages, typically they all upgrade together. So if you click on this change log, it takes you to our GitHub page, which would provide you features, what changed, what's the breaking changes, and identify all the different things that you have added to the package since we have upgraded as well. So it's a good starting point. Again, if you go to this link, or if you go to doc.brainchipping.com, it will land you on this MetaTF page, and you can start building your stuff out for Akira. So, getting into the three different Python packages, you can view Akira Python package as an interface between building the model that you've built out for Akira, and a use your interface for running it with our hardware, with maybe with our IP, or with our the board that you've provided with our chip on it. CNN to SNN is used for conversion of your networks to a spiking domain, and also used for quantizing your networks down to 4 bits. And I'll dive a little bit more deeper into that. Again, model zoos contains our pre-trained networks, pruning technologies, knowledge distillation, so on and so forth. So when we look at the Akira Python package, it also contains a software backend, which is our simulation environment. So let's say you don't have the PCI card with you, you can still, once you've built out your models, you can still run them on the software, get your accuracies, get your metrics for your models using the software backend. So that way, your development can all stay in whatever framework you're using, or servers or systems you're using. And once you've done with all those things, you can run it on the hardware, and now you can get the performances benefits of the hardware. So in terms of power, or in terms of FPS, latency, so on and so forth. So that's how these packages work. And Python is really an interface that gets connected to our engine library, which is written in C++. And essentially, why we use Python, why we recommend Python right now, is because typically we evaluate our hardware a lot. So it contains a lot of these features that helps you to evaluate the hardware, or capture power information from the board, etc. Engine library is something that we typically customers who license IP, they get it, they can compile it, so they can skip the interface of Python and run their entire application using C++. So just kind of putting it out there that we do have an engine library that is in C++, and we have an abstraction layer, or we can convert that. We have an interface that gets spoken from Python to C++. CNN to SNN, if I talk about the typical conversion workflow, you have a Keras CNN model. You can check whether, before even you begin converting or training your model, you can check whether that model is going to get compatible with Akira, or if you need to change your architecture somewhere down the line on maybe there are some restrictions on kernel sizes, etc. You can change that beforehand before you can dive into the extent of training these models. The next step is, you train your Keras model traditionally. You do it in the normal workflow. You have an entire machine learning pipeline. These are float models typically. So that's the blue section out there. Then once you've optimized your network, or let's say you begin with a pre-trained network of float, you can quantize these models, right? And you can quantize them up to 4 bits. So 1 bit, 2 bits, or 4 bits, all the way down. Or you could have mixed precision layers as well. So, your top layers could be 4 bits in weights, and your last couple of layers could be 1 bits or 2 bits, depending on the performance that you're targeting for as well. And again, we quantize not just the weights, but we also work on activation quantizations as well. So again, mixed precision for both of them. Just keeping in mind, your input can be 8 bits and can be 4 bits or lower. But everything after that as an input to different layers, which is the activation section of it, that needs to be 4 bits or lower. So that's one aspect of it. So what you'll typically notice is once you quantize your model, there would be some degradation in performance in general use cases. And so because these models are in TensorFlow, you can train these models again on the same machine learning pipeline. So you can, on the same data set, you plug out your float model and you plug in your quantized model. And so this training now is a little bit different. You don't train it for the original duration. You probably do it for a couple of epochs. And then you can regain any performance drop that you have got with direct quantization. So this process is typically called quantization-aware training. And so this helps because you've chopped out your bits, so much. This helps your model to readjust its weight to just use 4 bits of value. And that way you can still get the required accuracy, even by chopping these bits off. The last step is the green block, which is now you've done your entire optimization, your float optimization, your quantization optimization. You're ready to convert into Akira, into an SNN network. So again, CNN to SNN offers this conversion API that helps you to convert these TensorFlow models to Akira. And what it does is basically just one-on-one weight-to-weight translation. So we have respective layers for your TensorFlow layers, and we're just translating those weights into the SNN network, and which is why we don't need to optimize these networks further down. So you still get the same performance in terms of accuracy, even after this conversion step.
Yeah, one thing I want to say too is, most of the time people are training for large data centers and they have unlimited compute there. This is really meant for an edge-based device. So when we quantize down to 4 bits, that means we're using, as opposed to 32, 16, or 8, means we're using, 1/8, 1/4, 1/2 the memory that you would have on a larger model, which means faster latency and lower power. So we are an edge-based device with limited resources in the real-world use case that you're targeting. And that's why we quantize down to 4 bits.
So moving on to the last package, which is our Akida models package. Again, I mentioned these are pre-trained networks. So when you download these networks, you get in TensorFlow environment. So you can either get quantized models or you can get floating point models. And we typically use them for transfer learning, right? And you can identify which model you want. We have listed them on what data sets they are trained on, whether it's ImageNet or if it's a medical use case, you have some medical models on medical data sets as well. But the important factor is these are TensorFlow models, so you don't need to necessarily optimize it further in terms of architecture. You just need to implement the process of transfer learning. And so if you guys are not familiar with transfer learning, it's just you are replacing maybe your last layer with your use case, and just retraining the network, freezing everything else, or retraining the entire network again for fewer epochs on the newer data sets, right? So that way um, you can be assured that these models, once trained on your data sets, can convert and will work on Akida. And just to note that these networks are highly optimized for our Akida hardware, meaning there are, let's say you take MobileNet out of our model Zoo, and you compare it with the MobileNet that you get out of TensorFlow Hub, you might find subtle differences in those layers. And it's just purely because the way our hardware functions, and there are some layers that work quite efficiently on our hardware. You get more performance out of it, or lower power out of it, yet getting the same accuracy on the original data sets, right? So that way you're starting off from a highly customized, highly optimized network that our engineering team has built out for. And we keep on adding more and more models with our package. So I think few months back we had a couple of less models. We added 2-3 more models to this model Zoo. And so there are a lot of models being cooked up in the background, and there are, until it meets the criteria that we aim for, we don't put them in our model Zoo for public use case. But that being said, keep an eye out for them whenever there's a new version out there in MetaTF. Probably a model is also added as well. So keep an eye out on that.
There's a question here. I'm just going to read it. It says, how do you test the converted model, especially with respect to all the functions working on the board? So you probably want to go over.
Yeah, so I have a tutorial that I will talk about in later slides, and that will show how do we convert a model. It's again using our CNN to SNN API, one of the APIs in the package. It's called a convert API that will just help you to convert these models. It's probably coming.
Sorry to interrupt. My question is specifically when you're trying to use TensorFlow Lite model, like the bigger model which you're trying to use, and you convert the quantization model to using TensorFlow Lite, right? So when I did with unit, some of the functions inside it, like specifically transport convolution function, wasn't getting optimized. So is there any specific thing which you're writing to make sure that all the functions in the unit are getting converted, quantized, especially converted in the sense?
Yeah, I think I like to mention we're not using TensorFlow Lite for quantization. So there is a quantization package in TensorFlow, and even in our CNN to SNN package. So you would have to use the quantization API coming in this tool set, in the CNN to SNN tool set. So there is a quantize API that you would use, which supports 4-bit, 2-bit, and 1-bit. So TensorFlow today, their default quantization is only up to 8 bits. So what we have done with that interface is we've extended those classes, we've inherited those properties in the classes, and we've written some algorithms, maybe some custom ones as well, to support 4, 2, and 1 bit for waits and activation modes. So in order to work with quantization for Akira, you would have to use our CNN to SNN package and the API that comes along. Again, even when you, let's say you saved an entire model, you need to load it back. Make sure you use the API within the CNN to SNN to load the model back as well. Because if you load it the traditional way in TensorFlow, your quantization will be restricted to 8 bits. You will not inherit the classes or properties of 4 bits. So make sure you also use our APIs in CNN to SNN to load these models back. And again, to list out all those APIs, if you kind of click on those sections that I showed you earlier, you'll see a bunch of them. You'll see some bunch of documentations as well. So try it that way, and maybe that will work for you.
Okay. And like one more also question I have. So how do you know like all the functions are working or not? I understand the answer which you're trying to give. So, but when you use Vela compiler, like that's what we use generally with TensorFlow Lite models. So once the CNN is to SNN model converts quantizes a model. So now I have a model Lite file, the bigger the version of the smaller file which I'm trying to talk. So how do you compile it? Is there any specific tool which we can compile in this API?
Yeah, so you need to get out of that TensorFlow Lite. We don't use TensorFlow Lite with Akira. We use the standard TensorFlow framework and the CNN to SNN in order to quantize and convert. So when we convert these TensorFlow models to SNN, we have APIs embedded inside that, which optimizes your quantization models and also converts them to SNN. In order to run those SNN models on, let's say, on the software backend or on the chip, we have those engine libraries. Those are compilers that we have written, essentially that gets connected to the hardware, and you can run these models on the actual hardware as well. So we have our own engine library that we have written in C and C++, and which is what we use to run these particular models. So you're not using TensorFlow Lite in any case in MetaTF. We are not in that world for using in Akira.
No, I'm keep on asking about TensorFlow is like I'm just making sure to compare with the TensorFlow and Akira so that I can make sure the information going into my mind is clear, and I can.
So again, at this point, right, when you are at this stage of you've trained a float model, and let's say you have another hardware that uses TF Lite, and you have Akira. So at this point, you have two different junctions to go for. You can use the TensorFlow quantization and TF Lite processors for that hardware, and this is for Akira. You're still running the same architecture on both these different hardware, and you can make that comparison on, okay, what is different, how is it different, what benefits am I getting, and what disadvantages am I also getting.
Yeah, okay, got it. Thank you.
Yeah. I would like to actually go to this CNN to SNN tutorial. Let me just bear with me. I would like to stop sharing and come back. If you see this example, again, it's available on our MetaTF framework. It's a very simple example just to explain the process of quantization and conversion, the same thing that I talked about earlier. So many things are skipped in here, which are very standard. So let's say you're pre-processing your data set, you're loading them, which is this particular section out here. One important thing to note, what we've done is there's an input scaling, right? So because let's say in this example, we will be just scaling from 0 to 1 and not -1 to 1. When you convert that to an unsigned 8-bit, it represents in 02 to 55 format, right? So that's the rescaling factor that is taken into consideration. So if in case your model has a different scaling, let's say you go -1 to 1, this rescaling in an unsigned 8 will probably be, from 127 to -127 to positive 127, right? So that's what you need to be kind of keeping a check of whether your input scaling is equivalent or not. This is important. Why? Because during the conversion step, you need to provide this scaling factor to your Akira model, because we take in unsigned 8 as an input data. And if you have a different scaling measure, which is different from a default measure, right now it's 0 to 55 as a default. If it's different, then we take care of that scaling internally on the hardware. So you do provide an unsigned 8 input database, input data sample. But depending on your input scaling, those scaling for your input will be readjusted before the first layer is being hit on our hardware. Again, this is very standard. You're defining a model. Let's say you use a pre-train or you define your own model. I'm not going to go over this step. It's very common. I go over this API. Actually, is this size okay, or do you want me to zoom in?
It's okay.
Oh, okay. I didn't ask for that before. So if you use this API, it kind of tells you whether, hey, if the model is good, compatible or not. If it's not, it'll probably give you a list of why is it not. And in many cases, it works very well, but it might miss some edge cases, which you can also find out during the conversion process as well. But it's a pretty good API that works very well with this scenario. Training, which is very standard, whatever loss you use or whatever pipeline you have, or you have a different custom loss as well. It's very standard using in TensorFlow. Not go into that details yet. Yes, but I would like to see, okay, I'm getting, in this example, I get about 98% of accuracy. So just keep a pin on that so we can see, okay, well, how does it compare in Akira and quantization as well. So quantization, I mentioned to you, we need to use one of the APIs from CNN to SNN. Let me just zoom in a little bit. CNN to SNN. So if you see, we are importing that API from this package. There are 3 different parameters to look at. So input weight quantization is what is your quantization bit level for your inputs that you will be given to a model. I mentioned it can be 8 bits, which is what this is in this case. And everything else after that, your weights of the model, we quantize it down to 4 bits. And the activation quantization is also 4 bits, meaning intermediate outputs and inputs of layers are all up to 4 bits. So at any point, you need to capture the intermediate data, do some processing maybe on the host or give it back to Akira. Make sure that you're getting that 4 bits, and you can also supply that 4 bits back onto Akira as well. So now when you look at the summary, what you'll notice is you still have all the same layers, but now they are defined a little bit differently. They are all defined in quantized RAM, which is why I mentioned to you, whenever you load the quantized model back, please make sure to use CNN to SNN, because these types of layers needs to be loaded back. You need to be able to support 4 bits, 2 bits, and 1 bit, which is currently only available with MetaTF CNN for Akira. So now when I check for accuracy, I've not done any optimization. I've just chopped those bits off. So I see I get 83% accuracy, right? That's like 15% drop from a float model. This is something that I don't want, right? I want to optimize it further. So that's where, the quantization aware training might come into place. Okay. Before I go into that, there's this API called quantize layer, which, after, let's say you've quantized everything down to 448, for example, there is certain layers that I want to quantize differently. In this case, I think the ReLU one, I've set it as 1 bit, and dense I set it as 2 bits. So I can individually go and pick what layers I want and have a different quantization level set for them. So again, after when I see it's a miserable drop, it's like 11% right now, which is not doable at all, which is where the step of fine tuning comes in, quantization or weight training comes in. But notice the advantage here is you're using quantization, so you're already using less bit value. And so you'll see if I'm able to get the same accuracy, there's huge benefits of that. So again, I use the same fit function in TensorFlow Keras over the same data set, but this time you're using less number of epochs. I might have a different learning parameter as well. Depends on the complexity of the data set, the complexity of the model, and the complexity of the use case as well. So let's say I'll skip all the steps and let's check out the accuracy. Again, I get 97% accuracy, and I didn't optimize it further, or I didn't do any special training. I just trained for like 5 epochs. If I probably train it for 10, 50, 20, I might hit 98% as well. But this is kind of just an example, right, to show what is being done. So this way you can regain the loss in accuracy. Okay, so the benefits here is your entire network is 4-bit, and your some last 2 layers is probably 2 bits and 1 bit. So you're working with a lot less bit value. And because of this, the size of that network is also drastically reduced. You get much more latency. You can just on the software level, you get a much more latency, right? And when you use it with a special hardware like Akira, you get many benefits out of that. If you compare it with a standard GPU that takes in float model, or even let's say takes in float 16, for example, or even 8 if there are some hardware out there that does that, you'll see a noticeable difference in just if you have the same hardware, you'll see those noticeable differences, right? But now you have some specialized tricks to do, you'll see a lot more difference out there as well. The last step is the conversion. In order to run it on the simulator or on the Akira hardware, we need this conversion step, right? So again, CNN to SNN is used, convert is used, and remember the input scaling that I talked about, right? Default is obviously 0 to 55, and if you have a different one, during your conversion, you're just presenting that, hey, I trained my model with this sort of scaling, in this scenario. So that way, when we run these models on Akira, we know that the inputs that you're providing needs to be scaled of a certain factor. So again, when I check my Akira model and let's say I check for accuracy as well, I still get the same accuracy, right, as my quantized model that I saw earlier. This is because again, it's just 1-to-1 weight translation. And now we notice the summary as well. You'll be wondering where all the probably the ReLUs or batch norms, everything went away. It's still being applied. It's still being applied in these sections. It's just that these definitions now are of our SNN layers that kind of easily interpretable as well. So in terms of convolution, it might have a ReLU in between. It might have a max pooling if that's the network that you also used. And all the batch norms that you use get folded back into the previous layer. So you still are kind of gaining the entire purpose of your architecture and are going through all of the layers, even in an SNN kind of framework.
You might want to mention this, verify or to emphasize, this is running on MetaTF on the simulator. It's not running on the hardware.
Yeah. So once I run this, this evaluate as well, notice I actually ran the Akira model. So it's that simple to run it on the simulator. That you don't need to make anything special to run it on the simulator. There is something special to run it on the hardware, which I'll go over in the next section. But you just, once you convert it, you just, can run it, and it will use our simulator back and recognize that, hey, I'm running it on the software. Even in the summary, you can identify whether this model is running on the software or it will be on the hardware. There'll be a different description if you try to map it on the hardware and try to run it on the hardware as well. So there'll be a significant distinction between the two as well. So again, I'd like to jump back to the presentation. So I'll stop. Okay. So at this point, do you guys have any question on the flow that I talked to you about and the infrastructure before I move on to running it on the
Here's
hardware?
a question here is there any process for continuously retraining the model with different data?
So are you talking about, after you converted the model to Akira, or it's just in TensorFlow? If it's in TensorFlow, it's just probably transfer learning again and again on new data sets, or you're trying to do reinforcement learning, you can probably do that as well. With Akira, we have one-shot learning, that allows you to learn a new sample of the model that you've already converted, right? So I'll go that example probably in the next lecture, but those are the two key differences in looking at transfer learning and probably looking at one-shot.
Have we seen a demo for the one-shot learning?
Yeah, we've seen something.
Right.
Yeah. Does that make sense? Who will ask the question?
Yes, that helps. Thank you. I'll be looking forward in the next session.
So yeah, go ahead.
Yeah, how did you split your data? What is the percentage of training and testing?
Oh, in that example, I don't really remember. It probably might have been mentioned. So if you can check that out, that'd be nice. But typically, there's no difference. Like you probably, developers do 25, 20, 75, 25 split, 20, 80 split, or 30, 70 split. It's dependent on what your training looks like. But that example is to primarily show what is quantization, how do we do it, how do we do it with CNN to SNN, and what is QAT, how do we do it, and how do we convert the models to SNN. That's the primary goal of that tutorial. It's not to teach you about the training process in TensorFlow.
Another question here. I do not think there will be any high difference in accuracy when run on software indirectly Akita hardware. My guess is that it'll be more latency and performance differences. So just curious, what is the overhead of these software simulations, and can we use both software and hardware to do inference on multiple data points?
I would say that's a very, very good question. So yes, you're right. There would be no difference in accuracy. You'll see improvements of power and FPS when running it on the hardware. What's the key difference? It's the way the software simulator works. When we run it on the software simulator, even though we're just using 4 bits of information, the memory that it stores, it actually stores for 32 bits. Okay, so when you are inferencing on the software, it's taking all of that 32 bits, truncating it down to 4 bits, and then running it on the hardware. That's one of the key differences that you'll notice that, okay, why is that such a lag? And you still get the same accuracy because you're using the relevant information that we need. But again, with the hardware that takes in 4 bits, run the computation in 4 bits, does not take that truncated account, and does not take 32 bits, that's a huge difference. The second difference is the way the computation happens. I think in the previous lecture I showed you what is event-based convolutions. So we skip those non-event values, right? We don't pass in entire activation maps within Akira. We just pass in events and propagate that information forward. When you're trying to do it on the software, you need to make sure that you're skipping those zeros, and you can't really operate the way the hardware operates. You can only simulate the way the hardware operates. And in order to simulate, you might have to write some extra checks or some extra APIs to make sure that you're simulating the way the hardware would simulate. And that's one of the 2 key differences why there would be a difference in the simulator, and why you need the hardware to work for these models.
Yeah, thank you for that. But I just was also curious about, for example, I have the PCI Akida chip that you guys sent, and I'm okay. There's a third question, but if I somehow able to integrate to a Raspberry Pi for any particular use case, then on the Raspberry Pi compute engine, I can do some inference using the software part of it, maybe for the use cases on which the latency is not a big issue for me. And at the same time, can I also use the Akida hardware to inference maybe totally different use cases? So can I think I will be able to do those in parallel, right?
Yeah, that's completely doable. But if I were you, I wouldn't be looking at that from a software standpoint. Why?
Yeah,
Because
I was
you
just
have
curious if
TensorFlow Lite
yeah.
frameworks, you have TensorFlow Lite Micro and all that to run on the host. They run very efficiently on the host. Our simulator is useful for checking whether your model is good and you're getting the good accuracy. It's not optimized to run on the host. So if
Okay.
I were that application, I would probably take that application in that host and in macro or something. Or I would just make sure that you can compile the model to Akira. Why not just run it on Akira, right? And if you have, let's say, multiple use cases, you can remap the model on Akira. So you can leverage the same hardware, run 2, 3 different models, and build an entire application that kind of uh, uh, makes the user feel that you have multiple models running in parallel. I showed you one example of an in-cabin use case where we had, a person walking in, there was a keyword spotting and all those. There were essentially 4 models being run in that demo, and we were running all of that on Akira. So the way we're doing is you write an entire application, make sure that you can take those frames, you have multi-threading being used, and there's a lot of software optimizations that you can make, and you can just reuse our hardware over and over again for different models, right? Because we are agnostic to modality, we're agnostic to different architectures, and we don't fixate one architecture to run on Akira. So that way you can remap different models that are compatible and run them on the Pi use case that you talked about.
Okay, just a follow-up question to what you just explained. So I believe then the hardware, like the isolation for the resources, especially when you pointed out a key difference between the software and the hardware, how the 32-bit mapping is still there on the software simulators, and how the Akida will map it to 4 bits. So for I believe to have equivalent performance for the same models, the memory isolations or the resource isolations in the hardwares are, I believe, are taken care by the hardware. That as an user of when we create these applications or these models, we don't need to map the isolation on the hardware such that we get equivalent accuracies for these models, I believe.
Yeah, I mean, once you map the model on the hardware, we take care of where the weights are being stored.
Okay.
How are they being computed as well. We have embedded SRAMs with our engines, so that way we store those weights, your input buffers, your scratch pad memory for when you do computations, where do I store the temporary information as well, right? So
Yeah.
we handle all of that for you, and
Okay.
just when you have the model, where are you storing on the host? Make sure you're just calling it, your the APIs you're calling it from that location, right? Like, okay, here's the model that I've kept on the host. Make sure you fetch in the weights from here.
Okay. Thank you.
So running it on the hardware, it's a very simple process, probably 3 lines of code. So in this particular example, it's a keyword spotting example. So let's say I use a pre-trained model. It's currently in Keras. I converted that to Akira. Imagine you have already done all these steps, right? You have a model, and probably you have also saved it. You can get the reference of our board using this API, which is, you can connect multiple boards on a system as well, if provided you have multiple PCIs. So depending on what index of board you want to run, you get that reference. And the Akira model that you have, you use a map method, which is inside our, again, Akira package inside the model class. So use this method and you point out which device you wanted to map it to, which device you wanted to essentially run it on. Once you do that, again, when I print the summary, in order to verify whether it's actually done on how many resources, etc. is being used, you'll see the same summary is being printed out, except few minor changes. You see instead of software, there is hardware written. So okay, you show that okay, run on the hardware. There are engines column provided as well. So every layer, how many engines it will be using. In this example, we just use one engine for every layer, but different examples, you might have multiple engines for different layers as well. So you kind of a good ballpark, you get estimations of this is how stuff will run if you're going to run this on this particular hardware. You can also capture size information. So if you are ever going to be saving the model, you know how many bytes or kilobytes of information you need to have on your system to make sure that the weights are being stored properly. So let's say you map this model. In order to infer over, you can again call the same APIs, forward, evaluate, predict, depending on what you use. Once you do that, you notice a significant difference in FPS, in running these particular models, because you're now using it or running it on the hardware. Yeah, otherwise, if you don't have the hardware, probably it will throw you an error in this scenario itself. So you will not be able to run it on the hardware at any time. Again, there's a slight difference. We can run your inputs in batch sizes as well. So there's a different mode called sequential pipelining, which I'll explain in further slides. But essentially, what it provides you is more throughput if that's what you need from the hardware. So you can run just like your GPUs. You can run in provide multiple inputs together and get more throughput out of that.
This is another one where because you're an edge-based device, you're trying to find the optimal resources for power and latency for that use case versus having a large data center running your AI inferencing and etc.
So how do we save these models? What do we do, and what is the comparison, right? So typically when you're using Python packages, we save it in an FBZ format. So the difference here is, let's say you quantize it, you already see a reduction in the size. You've seen this example, the same model, MNIST model, it's probably 440 kilobytes. When we save it in an FBZ format, we're doing another set of probably compression and serialization, which is why you see only 44 kilobytes of data. So, you are also having a further reduction in size of the model when you're saving this particular models onto this. So you can, let's say you saved it on the server where you trained it, you can have this model now on your system where your Akira device is and import that model back. So the next line just shows you give the location where it is, and again with our this model class, you can just simply load it back into this variable model Akira variable out there. And again, if you want to run on the hardware, you call the map function and call the predict, and you're done. You run the model on the hardware. Now, this is something extra, which is something, if there are some people out there who will compare the size that we provide here compared to the size that you obtain here, there'll be a lot different. Why? Because in this, we have some extra information that we store in order to give you information like power or some other statistics of the model. When you actually go in the commercial environment, we don't need all that information. We just need to store the weights into Flash. So we just need those weights, which is what this size is all about. So the way we can do that is, again, these are essentially sequences. You can extract the binary out of that and essentially store in a .bin format, which is the file which only and only contains the weights. It doesn't contain any extra information at all. So you can actually use this, flash it on your system, and run it in a commercial environment, and probably also use it with just our engine library. You don't even need our Python packages to run this particular model, right? So just kind of putting it out there, if kind of as a general knowledge, that this is how you would be doing if you were doing it in a commercial use case for Akira. This is also an important point of reference. We mentioned we are an IP company, right? So I'll talk about the first two diagrams out here. Let's say you're running the Akira model, use the Python package, use the software backend. We already accomplished that. We have the Akira board and the chip. The way our Python package works, we run it with the engine library, and through the PCI interface, which is the current board interface, we can load these models and run these models on the chip. That's how the current workflow works. When you go into IP integration, now whether it's in a chip, just the same chip, let's say you have an IP embedded in this chip, or if it's on a board, if you have this PCI board and you have some Akira IP embedded into it, that's where these integrations would occur. So when you look at that integration, you have, let's say, an application software that helps you to communicate with the chip. Within that, we have our engine library compiled for the host OS, whether it's, let's say, Linux based, whether it's bare metal, RTOS, whatever it is. We are host independent, so we can compile our engine library to respective host. We just need the compilers and make sure we can compile it. And the moment the IP is there within the chip, this engine library, it knows where the IP is located, where do I need to look for memory in terms of weights, where do I need to look in terms of storing the inputs, outputs, etc. That's how we write an infra layer, which is an hardware abstraction layer that kind of communicates our engine source code to the IP. So that's how, in a commercial aspect, when we sell IP to our customers, they embed the IP within the chip, and we have our engine library, which they embed within their application software that can run numerous other things. They can have numerous other, let's say, neural networks. Some people talked about TensorFlow Lite. You can have TensorFlow Lite micro as well for many of these things, along with our Akira runtime as well. So that depends on the customer on how these integrations work. But essentially, this is the flow of what customers and what the commercial world will look like for Akira. So this is kind of a step forward in terms of how developers can first evaluate our technology using the Python interface and our PCI interface and our boards in order to go to the next step of making sure the IP and everything works. We know the same model that you're running on the PCI board out here, you can run the same particular model on this IP integration as well, because you are essentially communicating with the engine library in order to run these models on the IP. So let's continue. So I was talking about running it on the hardware, maybe getting more throughput, running sequentially, running pipelining. So right now, on our board, we support that, where you may have use cases or applications at the edge where you need to run just one frame at a time, or you can collect probably 5 frames, 10 frames, and compute all of that at one time. We support all of that, and what we get is more throughput, right? So the way we get it, let's assume we are running 1 frame at a time for your architecture. So what happens is, essentially, see where my cursor is. Yeah, So essentially, the frame gets passed to every layer one by one, depending on the distribution, obviously. So 3 NPs, 1 NP, 1 NP, blah, blah, blah. So what happens is, because now you're using less engines as well, even the power observed is different. So typically, if you try to just measure power for one frame, you might not get the accurate answer just because it's so quick and so fast that you've not been able to measure the proper spike, or you not didn't measure how when it came back down, or so vice versa, right? So just to understand, this is how sequentially works. Once the frame is given, it goes through all of the layers in the network before a next frame can be passed. And again, the power would differentiate for every layer respectively. So you need to keep, giving more and more frames if you ever want to measure power. Like, keep on running your engine, keep on making it busy so that you can actually measure the correct amount of spikes coming out of it. Pipelining, this is what we call is, let's say you have, in this case, we have like 6 layers. So let's say you provide 6 frame at a time, for example. What happens is, let's say let's look at this example. Let's say in layer 2, frame 5 is being processed. The next step, when this processing is done, it then goes to layer 3. But now layer 2 is now processing frame number 6. So that way, within your entire model, you may have like multiple layers. You can always keep your hardware busy in processing some sort of a frame at a time. And this gives you more throughput with this particular feature, because now you're not waiting for the next frame to beginning processing in layer 1 while frame number 1 is still being processed, right? So you're not waiting for a longer period of time. So you can get much more throughput out there. And again, if you try to measure power, it'll probably be a very straight line, because all of the engines that are being mapped, they're all being consumed at the same time. So where is this used in terms of applications? It varies, right? Because if, let's say, this type of feature can even be used in streaming data where your data is constantly flowing. Why I say it can be used is because you could probably collect 2 frames, 4 frames, or 5 frames out of that. There is a step involved in terms of pre-processing. There's a step involved in terms of post-processing. Both of them, you do it on the hardware, on the host. Depending on the complexity of these steps, you might take certain amount of milliseconds or microseconds to process in pre-processing or post-processing. When you give all of the frames to the hardware and you get more throughput, the latency in compared to just taking 1 frame is significantly higher for all of these frames. So that way you can find a very fine line for many of the use cases where, while you're doing pre-processing of the current frames, your processing in post-processing is now being done and accomplished in the meantime. So you notice in sometimes in this online application, there's always a certain delay, right? And this is probably because of the pre-processing, post-processing steps, and maybe something else is being occurred as well. So you can always look at different applications, and it's totally dependent on the developer and how he's defining his application and how he's defining his entire code on making sure that I can collect certain number of frames, or I just need to pass it 1 frame at a time. It's totally dependent on use cases and the development of the project.
And this is really important when you get out in the commercial world, because you have to take in consideration everything. You want the most efficient system you can, and the more knobs you have to play with. As Nikunj said, I don't have to bring in 10 or 20 frames at a time and pipeline it all. I can bring in just the amount that keeps the engines all working efficiently, and low power. As I am cranking through more frames, and there's some center point that's the most efficient, and those are the tricks you can do with both the hardware and the software to ensure you have the most efficient system.
Right. So moving on, I've already provided a PDF. Probably if not, then we can provide it later as well. There are some tutorials that I would recommend you guys to obviously see. Reiterate some of the stuff that I talked about. Also talks about other use cases, how to transfer learn, how to look at, because you get quantized models from Model Zoo as well. So how is it different in transfer learning? Can you still implement all of those things? So it kind of just enhances and talks a lot more about all of these stuff that I just talked about. And this last link is Model Zoo performances. So basically, it takes you to our models, the data set was pre-trained on, the resources that you would require for Akira, the sizes, so on and so forth. So any information that helps you if you decide to go forward and use one of the models for your projects. Now I would like to move into the example section on just touching base on some of the very simple examples, but kind of highlighting how to look at that if you're looking at a large scale as well. So moving from audio to vision to vibration, I have a lot of these examples. So let's start with audio, which is in this case is just keyword spotting. So essentially, we have this data set, Google speech command data set. It's a public data set from Google. It has about 12 different classes that recognizes different keywords. There's also one class for just silence where there's no noise at all. And then one is like for unknown where it doesn't know what keyword you said, whether it's a noise of a dishwasher or background noise or drone or anything, etc., etc. So typically, there's different ways of making sure that you can implement these models. Now, when looking at Akira, we know that we need to operate convolution 2Ds. We know that we need to take in a frame-based type of inputs. So what we do is, in this case, even though the waveform is a 1D dimensional input, you can convert them into two-dimensional inputs. And there are a bunch of different encoding techniques that are out there for signal data and different steps that you can operate. One most popular one, I think even in the paper that Google published, they use is MFCC features. So just assuming that you have this audio waveform using or generating MFCC features, this is the pre-processing step I'm talking about. There are a bunch of libraries that does MFCC features, and every one of them have either gets the same result or is faster than the other one. Depending on what your application is, you would probably use either of them. But then you would be passing it forward to a network in order to make sure it trains, learns, and you're able to evaluate, right? So let's look at the example that we worked on. We used the same kind of approach. We converted that to MFCC. We just followed what the paper recommended. We didn't implement anything new out of the blue. We just followed what is the public information out there for these data sets and this particular model. So when looking at this model, we created the generic flow. The input was 49 by 10. We encoded that information. It was a 1 second sample. When we look at, the performance of this, we were able to get good performance in floating point. And again, we just quantize it, train it for very few epochs. We didn't even barely optimize it, and we were able to reach 91.9%, right? We're working with customers where we're using similar use cases. We are making sure that we're optimizing the model for their data set, because eventually you will only be transfer learning. You just need the good quality weights to transfer learn on a good commercial data set. So there's no point on optimizing this even further and putting all these efforts out there. But this is important, right? Because now you have a 4-bit model that is compatible with Akira. You can run it in a very low power environment, and you're getting a good accuracy out of it. One of the information is activity sparsity. So you remember when I talked about, in the previous lecture, you have activation maps, you have ones and zeros and some other event values as well. So what this means is when I look at this architecture from a layer to layer basis, my entire architecture has 61% less number of events, which means I just have 39% of event values to compute. So I'm not doing 50% less compute, I'm doing 61% less amount of compute for this data set and for this particular model. So this is how you can look at things. You can probably go ahead, take your own data set and optimize just on this sparsity. Maybe make it the same architecture, same accuracy, but make this model 80% sparse, right? And leverage the architecture of Akira to be even further lower in power consumption, right? So that way you can, if you have a constrained device in terms of power, that's how you can probably identify and do it. If you want to optimize on accuracy or performance or so on and so forth, you have other ways of doing all of those
And it's
situations.
not just power. Remember, the higher the activation sparsity, the faster response time you get, or the lower latency.
So now looking at a vision type of, there's just again and always on, you identifying whether someone is present in the frame or someone is not present in the frame. Again, taking a public data set, COCO data set, not go into much into the vision. It's, everybody uses, it's very standard. We use like a MobileNet 0.25. Notice now in this case, the sparsity is just 32%. And this is because it's a kind of a binary class problem. And maybe this data set, this model cannot produce more sparse. And this is just out of the band. We didn't do any specializations in it. We still get the same accuracy as the float as well. Even though this is the case, we are still low power. We burn about, I think from 1 milliwatts to 20 milliwatts, depending on the FPS, the frames per second that you want to target. And these are real-time FPS that we target, right? These are not just 1 or 2 FPS. These are proper real-time 3200 FPS that we target. So that way, in spite of being less sparse, we still low compute. That's just because you're doing millions of these computes. You're doing so many computes in this model that even though it's just 32%, you'd have less amount to operate on. And obviously you use under other hardware benefits like local memory compute. You have 4-bit weights and activation. That also helps with less compute and faster computation. So all of these scenarios help in being much more low power. So just kind of giving 2 different examples of audio vision with 2 different scenarios in terms of sparsities as well. Looking at vibration. So this is again a public data set doing fault detection in ball bearing. So what this does is there are different types of faulty classes in the data set. So depending on where the fault occurs, you have different faulty classes and one regular class saying that everything is fine, everything works properly. So what you'll notice is this is more like a vibration type of analysis. You get signals out of vibration sensors. And so these sensors are, I think, sampled at 48 kilohertz, probably. So again, these are 1D dimensions, right? I talked about audio. There are different encoding you can do. This, we didn't do any special encoding, any special processing. We just took a segment of like 1024 points, reshaped that into 2-dimensional data. So this will be 32 by 32 and just build out our own 6-layer architecture, right? With this, we are able to get like 99% top 1 accuracy on this particular data set. And this model is about 50% sparse as well. So the key thing here is, there are different ways of looking at a problem. You could probably do this with a 1-dimensional model with a, let's say, Con 1D or LSTMs or RNNs. Just depends on what your implementation is, what you're targeting for, and how to look at. And I'm just giving you some examples of how we did it. So if you want to follow the same process, welcome to, or if you want to have your own, steps involved, it's this becomes like a starting point, right, on how do we look at these things in terms of projects and in terms of implementing it and building our models for Akita. One last use case is about nose olfaction. So this is now working with different sorts of sensors that does chemical analysis. And the difference here is instead of building like a CNN architecture, we went ahead and built like a native SNN. We didn't even do CNN quantization, SNN, nothing. I'll talk about that in the next slide. But the key thing here is, even though this is used, let's say this is kind of a one-dimensional data out here, there is still a pre-processing or encoding that is involved. So what in this case, what we did is we kind of binned the input data that is coming across the different time points. And there are different channels, different sensors, right? So you can just append that to different channels. In this case, there are 12 sensors. So your input is probably by 12 channels instead of having like a frame-based channel, like let's say 3 channel or 1 channel in terms of RGB and grayscale. These you can expect it as like 12 channels. And we binned it across like probably 64. I'm not sure about the value out here. But yeah, we just, that's a binning process that we did. Again, this is a binning encoding process that you could probably implement. It's very simple that we did, nothing special out here. And I think one more thing is, remember your inputs can be 8 bits, can be lower as well. I think in this case, when we did the binning, we clipped it probably to up like 6 bits. So instead of using 8 bits, we're just using 6 bits of input information. So that's another thing that, now you're compressing your first layer very, very quickly, and you don't have much to work with as well. So looking at the model, it's native SNN. We just use one layer, which is the dense layer. And why is it called CNN? Because the representation is kind of similar to what we have. But the difference here is, you notice on the left, you say it's 1 bit weight. So the layer is just using 1 bits of weights, and it's producing just 1 bits of activations as well. So you're building pure native SNNs out here, and you're doing on a 1 bit particular model out here. So in spite of that, we get a very high accuracy. We get about 98% accuracy on this particular data set, which is huge in terms of the complexity of the model that we use. We never use CNNs. We didn't use backpropagation, gradient descent, all these complex algorithms that are so beneficial for getting a good accuracy. So there are use cases that native SNNs building is beneficial, because you can hit the same accuracy but get benefits of compute in terms of power and FPS. If you compare this with a CNN model, you'll probably, on our architecture, you'll still be lower power, but it'll be significantly higher than a native SNN model. So depends on what you're targeting for. If you just want, this use case, you're able to build such a model out there, you're welcome to do that. Again, MetaTF supports this development as well. Akita package is where you will be building out this model and running this particular use case. So there are a couple of tutorials examples that can flow with this as well. So just kind of highlighting many different modalities, how we looked at it from a general scenario, just making sure that this is how you can implement on Akita. Obviously, there's a lot of involved in, you can optimize it further, you can build your own training pipelines, can do all those niche things that you want to do. But at the end of the day, we are a neural processor. We'll be accelerating any model that you have and making sure giving you the best support that, with MetaTF that can be given, and so on and so forth. So that's just putting it out there for all you guys out there who wants to build in many different avenues. We heard a lot of exciting projects last lecture about you guys are planning. So, depending on what inputs are, what use cases you will be looking at. You can think of this as a starting point if that's what you want to do. So with that, I think I would like to end this lecture with this slide. I know if you have the PDF, there are 2 more slides that are missing, but I'll probably cover that in the next lecture. It's going to be a little light one. In the next lecture, I think what we plan is going on into one-shot learning in detail on the learning process of it and how do we build those things. Just going into some additional features. And I think Tor has something to share in terms of IP. How do we look at IP? Like just kind of giving a general knowledge for system guys who are very much interested in system architects as well. So this kind of will be highlighting some of those aspects on how do we look at from a hardware science standpoint.